Hi everybody, my name is Travis Rainford and today I'll be going over the popreplicate node. So let's start at the very top of the node with activation. It is a binary switch, meaning that if it's greater than 0, it is on, and if it's less than or equal to 0, it is off. There is no partial operation. What you can do, however, is if you enter in an expression, for example, I have $frame modulo 10 equals 0, which means that when the frame number is divided by 10 and the remainder is 0, it switches on. And as you can see, let's restart this real fast. Every 10 frames, it switches on. You can see it flashing right here. Let's enter an expression such as $f greater than 48. Let's restart this again. You can see it goes on, and then at 48 seconds, right here, it switches on. Next, we have groups. What this does is specify which groups of points the node operates on. If left blank, it operates on every particle that passes through it. Impulse activation and constant activation both work like the first parameter that we discussed. They're either on or off, and you can use expressions to dynamically activate them. They, however, do different things. Impulse activation spawns particles every time the node is cooked. So if you think of the sim as a loop, then every single time the loop makes it back to this node right here, it releases the amount of particles specified by impulse count. Constant activation spawns time based in seconds. This does not mean that the node is constantly cooked. It's still cooked once a loop, but rather that the node releases a consistent number of particles spread out over the time period of 1 second. Emit from attribute is useful for when you want to further control which points are replicated by giving points an attribute that dictates probability. I gave every single particle a random value, and we can use that to dictate which particles are replicated and which aren't. So I can see a lot less particles in my simulation, and every now and then you can see there's a lone one, ones that don't spawn any particles at all. Now, this is a big word for me, so bear with me. Probabilistic emission. Now what that does is that works on constant birth rate. It adds randomness to an otherwise predictable spawn rate. It spreads out the birth rate so that it's not always 100 particles a second, but it will average out to 100 particles a second over the course of the simulation. Just born group, right here, is a group for particles that were just born. This parameter is simple, but it can trip people up because when it says just born, it means a particle is only in this group for one subset, but then it makes way for the next batch of particles. The seed determines which arrangement of points and attribute spawns. When you change the seed, you change the way the particles spawn. There we go. Kill original particle means whatever particles are fed into this node will not make it out. They will be killed at the end of it. Jitter birth time and interpolate source work together to add variation to the spawning of particles. It looks at the position of the particle at spawn time, and then it cranks it back a little bit. It says, what if this particle was spawned a step earlier or a millisecond earlier? To better show off the shape and noise tabs, I made a second simulation where there's a little less going on. So starting with the shape drop-down menu, the replicate node gives you a couple of options. Starting from left to right, we have cube, sphere, cylinder, cone, grid, circle, and line. Grid, circle, and line are 2D shapes. Weird situation going on there, but as you can see, they're 2D shapes. And because they're 2D shapes, orientation is no longer grayed out. Because with the 2D shapes, what you can do is you can choose which axis that the particles spawn along. Now, moving on to center. Center is the origin of the point cloud. And by the way, this is the point cloud. It makes more sense if you think of it more as like an offset. For example, if I was to move this 3 units in the positive x direction, you can see it spawns shifted away from the original particle. You can see the original particle falling down there, and then you can see where the point cloud comes to spawn. There we go. Let's move that back. Size and uniform are similar. They both change the scale of the point cloud. Size allows you to control the scale on a per axis basis. For example, say I now want this to be 3 units wider. As you can see, when it spawns 3 units wider. Uniform scale will affect all 3 axes at the same time with the same value. Sorry about that. See, 3 times bigger in all 3 directions. Let me change that back. Velocity stretch is not a parameter that I use all that often. What it does is it scales along the velocity vector of the particle of the original particle. So as you can see, as of right now, our particles have a velocity of -9.8, And so it is scaled negative 9.8 in the y direction. And of course, velocity scale affects how strong that is. So if we crank it down, it's not as big. And if we crank it way up, it's much bigger. So if we go over to our right and we add noise, you can immediately see a difference from the round sphere that we had falling before. Now with the popreplicate node, you get a couple of different options. Each of these noise patterns have a different way of generating their values. For the sake of this video, we're going to stick with simplex, but I would experiment with all of these. Moving on to the next parameter, frequency. What frequency determines is how many different values are generated on a given axis per unit length. And so what will end up happening is when you increase it, what you'll see is you'll see more variation. Like it looks fuzzier because there's just more values being generated on a given axis. However, if you go down, oh, no, I want this one. If you go down, let's go down to 0. No more noise is generated. And this works on like an absolute value basis. So if you were to go negative, just more variation, same as if you would go positive. But we're gonna drop this down to 1 more time. Offset. So offset isn't very confusing. What it does is it determines where in the noise pattern you're getting your values from. If that's a little difficult to understand, imagine it like this. You have a frame, you move the frame, you can capture a particular part of the pattern. And so to demonstrate it right here, you can move this, it changes the noise that you get. Oftentimes what you'll see people do is they'll animate the offset, and so that'll give them a different part of the pattern every single frame. Amplitude. Amplitude is fairly easy to understand. It's how strong the noise is. Roughness changes the rate at which the values change. So a higher roughness means that you get a bigger rate of change. For example, one value might be 0 and the next value might be 10. That's a big rate of change. That's high roughness. There we go. Likewise, if you go lower, that's a smoother rate of change. And so instead of going from 0 to 10, you might go from 0 to 1, and you'll get a smoother looking shape. Now, if you really crank roughness up, you start getting something a little crazier. Attenuation is a dampening effect in which it changes how high the extremes are. And rather than change, it dampens how high the extremes are. The higher the attenuation, the less extreme the spikes are. The lower the attenuation, that's where you can start to get some kind of crazy shapes. Like right there. High extremes. Turbulence is like a macro level noise. So if you were to crank up turbulence, it moves it more. You crank it down, not so much. So the next tab that's important to understand is the attributes tab. And so for our first parameter, we have inherent attributes. And what inherent attributes means is that any attribute values that the original particle has will be copied on to the replicated particles. And so right now we have an asterisk. And what asterisk means is that any attribute value gets copied over to the replicated particles. However, let's say we don't want color. So let's reset the simulation real fast. And as you can see, it's a little hard to see. You can see the particles right there. They spawn in black, but they don't inherit the purple color of the original particles. Next is initial velocity. So initial velocity is important. This is also, as you can see here, use inherited velocity. What that means is that any velocity that the original particle has at the time of replication will get added on to the replicated particle. And as you can see here, the replicated particles fall slower than the original one. That's because of this pop drag that I have right here. However, at the time of replication, they do have the same velocity as the original particle. And you can change that. So what you can do is you can add to initial velocity. And I added a little 100 value right there. And you can get some pretty cool effects. So what we have here is that when the particles are replicated, they have a velocity of 100 in the positive y direction. And so they shoot up. They shoot up, then gravity slows them down, and then they fall back down again. So you can get some pretty cool effects doing that. Oh, sorry, let me close the geometry inspector real fast. Let's go to set initial velocity. And what this will do is same thing, really. Well, not the same thing, but it's different. So this is no longer reading the original velocity of the particle. It's setting a new velocity. And so as you see, as the original particles start falling, let's make this, no, let's keep this 100. Let's make this 50. And now you get some pretty cool slanted effects. And let's make this, why not? Negative 30. I have nothing to lose. So yeah, you can get some pretty cool effects doing that. Variance is like plus or minus 1 in any given direction. So you can get some pretty big changes. Let's do plus or minus 20, plus or minus 25, and then plus minus 25. Reset the simulation. Oh, sorry, didn't mean to click that. Just simulation. And so yeah, so now it's more of a spray instead of a neat orderly line. All right, you guys, thank you for sitting through all this with me. That was a popreplicate node. My name is Travis Rainford. See you guys next time.